welcome once again to RF transceiver design course. We are discussing module 4 on active devices. In last class we have seen the capacitor associated with the MOSFET. We have derived the FT of MOSFET and Fmax. FT is the transition frequency at which your current gain is 1, and Fmax is a maximum frequency at which your power gain is equal to 1. We have derived Ft and Fmax. Now we are moving to the BJT. So as we know, BJT, it has a emitter, base and collector, and it is NPN. If it is NPN transistor, then there is a N substrate, P substrate and N substrate. It can be connected like this in the lateral structure. There are two types of bipolar transistor. One is NPN and PNP. Based on the doping, we can have a NPN as well as PNP. So when we are using NPN, means if we consider the NPN bipolar transistor, so for large signal, this is a collector current which is a function of IS function of VBE and V threshold voltage VT. So based on the voltage VBE and VBE, means this VBE voltage and the voltage VBC or VCE, any we can able to find out which region the transistor is. For cutoff, your VBE should be less and VBC is also on. So when VBE and VBC both are less, then it is a cutoff region. Then if your forward active, means in the forward active region, your VBE means VBE is greater than VBE on, and your VBC, so there is a on voltage VBE, that is a 0.7 volt we consider, and similarly for the VBC, there is a VBC on voltage. So forward active region, your VBE should be greater than VBE on, and VBC should be less than VBC on. Similarly, there is another region that is additional, that is a reverse active region, that is less than, it will be VBE should be less and VBC is a high, and saturation region which is greater, VB is also greater than VBE on and VBC is greater than VBC on. But when we consider the BJT, we work on active region. So generally there is a cutoff, saturation and active region, and we works on a active region where your VB is a forward bias and VC is a reverse bias. That is a positive. So this is a how BJT large signal analysis will work. Now once you have biased your BJT in the active region, then you can consider the small signal model. So for large signal characteristics, this is a current, and in saturation region here, so this is active region. In saturation region there is a slope, and this slope, if you try to extrapolate it to this point, then that is nothing but a early voltage, that is called as early voltage, and that early voltage you can find out the, you can also get the output impedance RO by using this early voltage, that is del IC by del VC. So your output impedance is also depend upon this early voltage, and this slope can also provide us the what is the output impedance when you are working in the saturation region. So this is a large signal characteristics you already have studied in your basic course. You can go more in detail, and now we will move to the small signal model. So when we consider the small signal model, there are lots of parasitics, and in RF we are more dealing with the capacitors, and as we have seen in the MOSFET also, how Ft and Fmax we can define based on the capacitance associated with each node. Similarly, here there is a collector. So, this is a collector, this is base and this is a emitter. So, collector is a wider region compared to base and then emitter. So, here there is a collector to the base, there is a one capacitor CCS, then there is a at output there is a resistance RC3, there is a capacitor that is a C mu between base and collector, there is a capacitor between emitter and base, that is a combination of C junction. So, junction capacitance CJE, and this is a resistance REX. So, there are various capacitors and resistor are involved when we consider the bipolar transistor. And if we consider what are the important resistor and capacitor, then this is a small signal model we can come, this is a final model in which there is a base resistance RB which is important, C pi which is a capacitor between base and emitter, and then there is a R pi which is a resistance R pi that between again base and emitter. There is a capacitor C mu, R mu, that R mu is here if we see. So, because there is a C mu, similarly there is a R mu that is parallel to the this base and collector. So, this is a R mu resistor, and due to because there is a current gain, so we can get GM into V1. This is a current gain, output impedance RO, and the capacitor between collector to source, and output resistance RC. There is also REX is involved, which is at the emitter, and the other junction there is a one resistor. So, the resistor R pi here dominates the input impedance at low frequency, but at high frequency C pi dominates. C mu is due to the collector base reverse bias diode capacitance, and CCS is a collector to substrate parasitics capacitance. So, there is a collector to substrate capacitance, that is a CCS, and in some process this is reduced by with an oxide layer. So, this C pi and C mu are a dominant capacitor, and C pi has a two component due to the junction capacitance, forward bias, and the diffusion capacitance. So, C pi can be written as a CJE plus CB. So, it is a combination of junction capacitance and the diffusion capacitance CB. So, this is the capacitor associated with the BJT, the way we have considered for the MOSFET. Now, we will try to find out the FT. So, small signal parameters of BJT is given by this, where GM is QIC by KT, it can also be written IC by VT. Your GM by IC transconductance ratio is given by 1 by VT. Your input resistance R pi is given by beta, which is current gain, by GM. Output resistance RO is given by VA by IC, which is 1 by eta into GM, and eta is a process dependent parameter. And collector base resistance is ranging from beta RO to the 5 times of beta RO, and CB, which is given as a time, this is a T tau f is a time for when the electron is moving in the forward direction into GM. C pi, this is a CB plus CJE, and where CJE is a emitter base junction depletion capacitance, and it is given by 2 CJE naught, and here VT is nothing but KT by Q, 26 milliwatt. If you are interested about detail of this all equation, at the end of the slide there is a references are given. You can go more for more detail, you can go to the references. So, let us see what what is the FT and Fmax for BJT as well. So, only the difference between BJT and FET, if you see the small signal models, the CGS is replaced with the CPI and CGD is replaced with the C mu. Your VGS in this case is VBE. So, if you do the same analysis, your FT, which is equal to GM by 2 pi C pi plus C mu. So, this is a transition frequency at which your current gain in BJT is equal to 1. It depends upon C pi capacitor and C mu capacitor and the transconductance of the BJT. If you find out the if you write in terms of omega t, which is equal to Gm by C pi plus C mu, and in if you find in terms of the time, so this is a frequency. If we see convert into the time domains, then we can get the tau t, that is a transition time, which is equal to 1 by omega t. So, we will get C pi plus C mu divided by Gm. So, this C pi is given by Cb plus Cje plus C mu by Gm. So, what you will get is Cb by Gm plus Cje by Gm plus C mu by Gm. So, this is a this can be written as a tau f plus Cje by Gm plus C mu by Gm. So, this is a different than this tau f is a different than the MOSFET that we have seen. Now, what is a tau f? It is a ideal time, it is a so it is ideal transit time even there is a forward bias, but you will also get CJE by Gm and C mu by Gm. Now, what will happen that when your current is more, at that time when your current is less, this, so there is a, if we try to draw the graph between Ft versus Ic. So, what will happen that at lower current this Ic is, as Ic is increasing, this will start increasing, and then after certain point of Ic current you will get it, this Ft is coming down, and this Ft is a function of Ic at lower frequency. This at low frequency, when at low current Ic, this will be dominant, and at high current this will be dominant. So, this is high Ic, and when there is a Ic is a low. So, this portion of the tau t is dominant at when there is a collector current is low, and when there is a collector current is low, collector current is high, this tau f is dominant. Now, this tau f, it is decreasing, this Ft is decreasing, that is happening because this Ft is decreasing, that means your tau f is increasing, and that is happening because of the base widening effect and Kirk effect in the BJT. So, due to the Kirk effect or base widening happening in the BJT, it is making the tau f high, and it is reducing the ft. So, in BJT this is specific to the BJT, that is why I mention here. So, Kirk effect is important. So, due to base widening at high collector current, there is a Kirk effect. So, that effect is called a Kirk effect, and due to that your transition time uh, tau f is increasing, and that will reduce your ft. So, this is what is ft of the BJT. F max also we can write the same as a MOSFET. So, here in MOSFET we have written F max, which is half ft 2 pi ft c. So, now it is a CBC, in this case RB plus RB by RO. But in this case RO is not there. So, because this is a BJT, so we can consider we can cancel this, or that RO is too high, that will reduce this term, and FT divided by, if we take this 2 also inside, square root of 4 pi FT CBC into RP. So, this is not 8 pi, because 4 will go inside, it is 8 pi FT CBC into RB. So, this is F max of BJT. So, BJT F max is also depend upon the FT, the base to collector capacitance, and the base resistance RB. So, this is I will just 8 pi FT CBC into RB. So, this is FT and F max of the BJT. So, in semiconductor device technologies, a device with a similar size but higher FT value is usually favorable choice of technology, because let us say if you are working at 40 gigahertz, and if your device does not provide the current gain or the power gain at this frequency, then how can it be useful? So, it is for device engineer, it is always they try to improve the FT, and as we are going for lower node technology, that FT is improving or increasing. So, that is because of that reason, the higher FT device can operate at lower power without compromising switching speed, and the device with higher FT have a faster switching time and higher power gain and better efficiency without any increase of power consumption. Because we already also have seen that FT is a function of GM, and if you try to increase the GM, let us say CGS is not in your hand, it depend upon the many device parameter, oxide capacitance, then width and length. So, this GM is as a designer, it is in your hand. Now, when you try to increase the transconductance GM, that means you need to increase the power, and that will again increase the entire power consumption of your circuit. So, or it has also limit, it cannot go beyond certain gain if you try to increase the power also. So, that is why here that higher FT device can operate at lower power without compromising the switching speed, and FT have a faster switching time, higher power gain, better efficiency without increase in the power consumption. So, FT for silicon germanium BiCMOS and RF CMOS has been compared in this graph. Now, this graph it is not giving the FT versus channel length graph, but it is a maximum applicable application frequency by geometry size. So, this has not considered FT, but we can consider the maximum frequency for silicon germanium, which is operatable, is higher compared to RF CMOS. So, same technology, if you consider 130 nanometer of silicon germanium BiCMOS or RF CMOS, the FT or workable frequency. So, FT of BiCMOS is in the range of 200 or 300 gigahertz. However, the CMOS does not have that much range. It will not be more than 120 gigahertz. So, that is depend upon process also and manufacturing company, because different technology has some variation. If it is the same node also, there is some variation in the FT, but your workable frequency generally will be 10 times less. So, if your FT let us say is 200 gigahertz, because we can never going to use our device at this frequency 200 gigahertz, we are going to work at around 20 gigahertz. So, this is designer analysis that it is better to work at 10 times low compared to the frequency where your current gain is 1. So, this is the maximum application frequency, which is this frequency, not FT, versus the geometry size, and in this case BiCMOS is much better compared to RF CMOS. However, if you go for the lower node technology like 22 nanometer, 28, in that case you can also achieve the similar FT to the BiCMOS, but your technology node is smaller. There is a limitation in BiCMOS also. We will see the limitation of BiCMOS as well as what are the benefit. We already have listed out the benefit, advantage and disadvantage of CMOS and BiCMOS in the initial slides. We will see more in detail also. So, for silicon germanium technology, if you consider this NPN transistor, and this is a base which is base width which is a WB. So, in order to have a higher performance, let us say demonstration of a FT greater than 500 gigahertz, and we are approaching to use up to 1 terahertz. The problem is WB we need to decrease, and that will try to increase the RB. So, the silicon germanium is a solution. What is the solution provided? That base allows for a higher FT without reducing the WB. So, we can keep WB as it is and your FT will increase. So, that is the advantage of silicon germanium, and it will provide the higher FT. If we see that a silicon germanium BJT is also called as the introjunction bipolar transistor, and germanium is epitaxially grown on in the base. We have seen the difference between HBT and HAMT also in the initial class of the module. You can go through the cross section of that, and this causes a strain in the crystal and causes an extra potential barrier for Hall's majority carrier in the base from the flowing into the emitter. What are the benefits of using this? Is it will WB is decreases, your number of carriers are increasing. So, if you try to decrease the WB, your number of carriers are decreasing and your base resistance will low. But your number of carrier, if you try to decrease, that is NE, your junction capacitance CJ also decreases. So, because number of electrons you have reduced, that we have also seen in the MOSFET also, that junction capacitance is also depend upon the number of carriers. So, as Cj is decreased, we have seen the formula of Ft, that is Gm by C. So, in this case your capacitance is reducing, your Ft, Ft will increase. So, the ultimately we are trying to achieve the higher Ft, and in silicon germanium HBT it can be we can get the higher Ft by considering the low Rb also. So, this is the advantage of HBT, silicon germanium HBT. So, in MOSFET, so we have seen the BJT. Now, in MOSFET, in advanced technology, below the 45 nanometer technology, pin kind of structure has been used. So, there is a source and drain, and this is a 3-dimensional view of FinFET, and this is controlled by the gate on the both side. So, previously we have gate is only controlling on the one of the on 2D second 2 dimension, but now it is a 3D. So, scaling of MOSFET below 45 nanometer has been done in order to lower the length of the channel, and the gate control is now improved. So, in the previous cases, if we try to reduce the length, the gate control is not sufficient. Now, in this case there is a gate control is sufficient, and due to that it is also to enhance the output resistance and lower leakage in the subthreshold. So, we can also have the improvement in the output resistance, and it will lower the leakage in the subthreshold. Mostly TSMC, Intel, all the foundries are using a FinFET in the lower node technologies, and that will be the one of the solution in the against the MOSFET against the BJT silicon germanium. Advantage of MOSFET always will be there in terms of the back end and front end together. However, in BiCMOS there are some challenges, but that can also be done. FinFET structure. So, if you try to see the layout, so this is a called a fin because it looks like a fin. So, this is a fin height which is given by h pin equal to W, and pin width which is a W, f fin is equal to thickness T of silicon. Then this is a gate length Lg. So, gate length only is this much. So, now length is reduced so much, but you have a better control of the gate compared to the technology that we are using than other than FinFET. So, this is how the bulk silicon MOSFET looks like, and this is how the layout of multi-fin layout has been looked like, where this is a drain which has a you can see it as a cross section also has been made, and these are the multi fins. So, there are many fins you can make, the way number of the way we can do the fingering in the bulk silicon MOSFET also. So, here gate straddles thin silicon fin forming a 2 conducting channels on the side wall. So, there is a 2 conducting channel, and multi-finger layout very similar to RF layout which we generally use in a bulk silicon MOSFET. You can go for the reference for more in detail. So, what are the advantages of BJT or MOSFET? For fixed current, BJT gives a more gain and high BJT transconductance. It has a precision in terms of multiplication, logarithmic or exponential function. So, more analog function are possible in BJT over the MOSFET. However, it is difficult in FET due to the processor temperature dependency, and here IS process dependent in BJT. So, we need to use some circuit tricks in order to get the better performance. If we try to see what is the advantage of BJT over MOSFET in terms of equation. So, we will take one example, that is, if there is a BJT and BJT has a IC current IC which is equal to IS e raised to QVBE by KT. So, if you try to increase the current in BJT, so if we try to increase current IC to 10 IC, means 10 times increase in the current if we want. So, this is a curve which look like this. So, this is a IC I by VBE, IC by VBE, and if we try to increase the current by 10 times. So, what is the change in the delta VBE? So, in this case delta VBE, we can write it down 10 is equal to exponential, because this IS will be cancelled out, Q into delta VBE by KT. If we find a delta VBE which is equal to KT by Q into ln 10, it will come around 60 millivolt, which is too small. So, this delta VBE, if you just change a delta VBE by 60 milliwatt, your current IC is increased by 10 times. Now, if you try to consider the MOSFET, it will be a different case. So, in case of MOSFET, if we try to derive, then we need to use ID which is equal to K dash, let us say 1 half mu n Cox is a K dash VGS minus VT whole square. So, if you try to increase the ID by 10 times, we can write VGS 1 minus VT whole square divided by VGS 1 plus delta change in the VGS minus VT whole square. If you try to find out the delta VGS out of this equation, your delta VGS will come around 1 volt. So, you see the amount of voltage required to get the same current, 10 times current, is higher in this MOSFET compared to the BJT. So, here there is an advantage for a fixed current. BJT gives a more gain compared to the MOSFET, and we will discuss more about active components, and we will summarize in the next class. Thank you.